So we're going to continue looking at data representation, and today we're going to look at histograms. Now, histograms and bar charts are very often confused, and we'll talk about the distinct differences between them. But let's start with this data set. This is some data that's been gathered around the heights of trees in a certain area. If we took the bar chart approach, we'll just make the height of each bar the frequency. So let's see what happens when we do that. So for the first bar, which has a width of 20, it has a height of 20. The second bar has a width of 20 and a height of 25. Now the third bar has a different width. It has a width of 10 and a height of 30. Then we have a width of 10 and a height of 25. And lastly, we have a width of 40 and a height of 20. The issue arises that when we look at this bar chart, the heights can be misleading. Because actually when we look, we're intuitively taking the area into consideration. When all of the bars have the same width, then the height is directly proportional to the area. But now that we have uneven widths between these intervals, the height is no longer the best indicator of the frequency. The area would be, and our eyes intuitively interpret area faster than we interpret height. The misleading aspects can be seen when we compare some of these bars. This first bar has a height of 20, and it looks intuitively, as if this last bar is twice the size, since the area is twice the size. So you would anticipate or expect that in between 160 and 200, there was twice the frequency as there is between 100 and 120. Similarly for the fourth interval compared to the second interval. The way that we deal with this and maintain the feature of the area representing the frequency is to use a frequency density. This is a scalar that indicates the height we should draw each bar so that the area is representative of the frequency. Okay, so to calculate the frequency density for each of the individual intervals, we're going to take the frequency and divide it by the interval size, or the class width. So in this first interval, we have a frequency of 20 and a class width of 20. Which gives us a frequency density of 1. So the first bar is drawn in between 100 and 120, and it has a height of 1 unit on the frequency density scale. The next interval, the frequency is 25, the class width is 20, that gives us a frequency density of 1.25. It should be slightly higher than the first bar. So in between 120 and 140, we go up to 1.25. For the third interval, frequency is 30, class width is 10, the frequency density here should be 3. And as you can see, the bar is thinner, but it's a lot taller. It's significantly taller. Okay, on to the fourth one. What's happening here? Frequency is 25, the width is 10, our frequency density is going to be 2.5. So once again, quite a tall bar. Doesn't mean that the frequency is high. We need to think about the area. Okay, and then just onto the last bar here. This is the widest of all of them. We have a frequency of 20, but the class width is 40. This gives us a frequency density of 0.5. This is going to be the shortest of all of the bars. So just because the class interval size was large, it doesn't mean that this bar should get a large area. Its area is now proportional to its frequency. Constructing a histogram is only half of what we might be asked to do. We're also going to need to demonstrate that we can interpret a histogram. We may well have a question like this. Estimate how many people are between 130 centimeters and 170 centimeters tall. We're once again going to use the fact that the area represents the frequency to respond to this question. Here, we need to find the area in between these two lines. All of the area within the histogram in between these two lines. Now, some of these frequencies we already have in the table, but the others we're going to need to generate for ourselves. So in between 130 and 140, that's a proportion of the second interval. But I'm just going to find its area individually. It has a width of 10 and a height of 1.25. The second shaded region, well, we already know that that is 30, but once again, I can do a calculation to get that answer. The third one, we already know that that's 25, but I can do 10 times 2.5. And finally, for the last one, once again, this is just a proportion of the final interval. The width of the section that I'm interested in is 10, and we know the frequency density is 0.5. So completing that calculation gets us an answer of 72.5. So in this specific case, the area equaled the frequency. An area of 72.5 represents a frequency of 72.5. Be careful though, the area is not always going to equal the frequency. More specifically, what we should say is that the area is proportional to the frequency, and we might need to use a scaling factor between one and the other. Here's very similar data, but this time round the frequency density was already calculated, and we would need to identify the scaling factor between the frequency and the area. So, just going to do some calculations here to show you what the area is in each of these intervals, or for each of these bars. So, just multiplying the class width by the frequency density, we get an expression for the area. And we have 8, 10, 12, 10, and 8. Those are the values that we got for the area. So the total area of this histogram, as it is represented, is 38. Okay, so I'm going to show you a technique where we can find that scaling factor, that constant of proportionality that will link the frequency to the area. I could use the entire area and the entire frequency to get an expression, but quite often you don't have all of that information. So let's focus on a technique where we just use one of these bars. We hone in on one of these bars. Let's just go for that first bar. We know the frequency is 20, K is unknown, but the area is 8. So through this simple relationship, we should be able to find out the scale factor K. The scale factor K is 2.5. So anytime I have an area, if I multiply it by 2.5, I will be able to find the frequency. And obviously this can be rearranged so that frequency divided by 2.5 will equal the area. So this scale factor will help us throughout a variety of questions. At A level, we can no longer assume that the frequency is exactly the area. What we can assume is that the frequency is proportional to the area, and then go ahead to find that constant of proportionality. One more way that proportionality is represented in histograms is when we're told the dimensions of a bar from the histogram, and we're expected to find some scale factors that will help us to find the dimensions of another bar. These type of questions are rarely accompanied by a histogram, and we actually need to produce a diagram of the bars that we're referencing and the scale factors as well. Be careful here because there are different measurements that need to be used. We might talk about the class width, but there's also the drawn width. We might talk about the frequency density, but there's also the height. We're trying to find the relationship between these. So for the bar that I have the information about, I'm going to draw a quick sketch. So 100 to 120 are the class boundaries, and it has a height of 10 centimeters. For now, I'm just going to draw a representation of a bar, which isn't even intended to be to scale. But I'm going to start to label it with some of its variables. I'll start by considering two ways to talk about the width. So firstly, the class width is 20, but we were told in the question that the drawn width is 5 centimeters. So straight away I know there's a scale factor here of 4. If I divide by 4, I will go from the class width to the drawn width. In a similar way now, I'm going to focus on the height. I know that in a histogram, the frequency density is on the vertical axis. Frequency density is always frequency divided by class width. So in this particular case, it's going to be 20 divided by 20. The frequency density is 1. Now I've been told that the drawn height is 10 centimeters. So once again, the scale factor between these I can find quite easily, and the scale factor is to multiply by 10. Okay, these two scale factors are going to be the key to solving the rest of the question. We're asked to find the height and the width of the interval 140 to 150. Let's start focusing on the width. I know the class width is 10, and I know the scale factor for class width to drawn width is to divide by 4. So 10 divided by 4 lets me know that the drawn width is 2.5 centimeters. I could have just looked at those and seen that this class width is half the size of the previous one, so the drawn width will also be half the size. Okay, sometimes intuition can kick in, but apart from that, use this technique and the scale factor to know exactly what the drawn width is. Okay, let's get back to the heights. Frequency density we can calculate, and that comes out to be 3, and we know the scale factor to turn frequency density into a drawn height is to multiply by 10. So I can deduce that the drawn height for this bar is going to be 30 centimeters. So if you use this technique in the same way that I have, you will be able to identify the dimensions of any of the bars in a histogram. Okay, so before you get stuck into some practice of your own, let's go through a couple of example questions. Here, firstly, I've just been asked to construct a histogram. First thing I'm going to do is to calculate some frequency densities by taking the frequency and dividing by the class width in each case. As soon as I've got that, I'm going to decide on the scale that I'll use with the vertical axis, and I know my frequency densities need to range up to 13.6. So I'll just make sure I've got a vertical scale that allows for me to get all the way up to 13.6. As well as the vertical scale, I'll just take care to make sure I have a range of horizontal values that match the intervals I'm working with in the first place. Okay, so our first bar goes from 25 to 30 and has a height of 11, a frequency density of 11. The second bar from 30 to 35, and that has a frequency density of 7.8. Third bar has a class width of 5 once again, and it has a height of 13.6. Okay, the fourth bar, the first one with a different sized class width, has a class width of 10. It goes from 40 to 50, and it has a height of 3.2. And the final bar, actually quite a shallow bar, quite a low bar, it goes from 50 to 80, so very wide, but not high at all. It goes to 0.2. Okay, so that's the histogram constructed correctly. Apart from constructing a histogram, we were asked to make a frequency polygon. A frequency polygon, once again, exactly how you did it in GCSE, you need to plot the midpoint and frequency density for each of these bars. Which basically means, once I've marked each of these, I'm just going to connect them with straight line segments. And this is the frequency polygon that you may well be asked for. Okay, so it lies directly on top of the histogram, just superimposed on top of the histogram. We get a bit of an idea of how steep the frequency density changes are from one interval to the next. Okay, and just one more, let's have a look at an example that doesn't even feature a histogram at all, but is asking you to demonstrate your knowledge of a histogram. So here the data is about a random sample of temperatures that have been taken, and they've been summarized into a grouped frequency table, and we've been asked firstly to give a reason to support the use of a histogram to represent the data. The top reason that we're going to use a histogram rather than a box plot to represent data is because our data is continuous. Box plots do not have continuous data and they have gaps in between the bars, whereas our histogram, there were no gaps in between the bars, our data was continuous. A secondary reason, but not a stronger reason, is that we have different sized intervals or different sized class intervals. If you are asked for multiple reasons, we'll definitely talk about the fact it's continuous first and then the interval size secondly. And in part B, we're asked to specify the underlying feature associated with each of the bars in a histogram. And now you've heard me say this a few times now, the underlying feature is that area is proportional to frequency. The area we use for each of those bars will be proportional to the frequency. Okay, moving on to part C. We're given some information about the rectangle or the bar that is used to represent the interval 16 to 18. We're told that it has a height of 3.2 centimeters and we're told it has a width of 2 centimeters. And then we're told that the frequency is 8. There's a lot that we can do with this and you can use the technique that I've already demonstrated, but here we're asked to show that each day is represented by an area of 0.8 centimeters squared. So in this case, let's just get an expression for the area in terms of the drawn height and the drawn width. So in terms of centimeters and centimeters squared. The area is 6.4 centimeters squared. Well, we know that this represented 8 days. So if we divide this by 8, we should get an answer for the area per day. And here the area per day is 0.8. This is what we were asked to verify and to confirm. In part D, we were given some additional information that the total area under the histogram is 48 centimeters squared, and we need to find what is the total frequency, what is the total number of days that this histogram represents. Well, to find the number of days, we should be able to take the total area and divide by the area per day. 48 divided by 0.8 equals 60. This sample, this histogram, was constructed to represent 60 days. Proportionality is a key all the way through. There's always some aspect of proportionality being used within these histogram questions. Okay, and we're just about finished, but before you move on to some practice questions, let's take a quick look at the specification and exactly what it is that students are expected to be able to show, exactly what the examiners are anticipating you will be confident on. While you read through that, I want to quickly remind you that it will be sensible for you to come back and watch this video at a later date, maybe come back in 2 or 3 weeks or before an assessment. And as you watch through the second time round, because you've done your practice, a lot of what you go through here should resonate with you much more. And you have a chance to really embed your understanding of the difficult concepts, the ones that have been flagged up as A star.